Hi, I am Sushma, working as Assistant Professor in the Department of ECE in Institute of Aeronautical Engineering College. In this session, we are going to discuss about the combinational circuit and adders. In adders also, we are going to discuss about off adder, full adder using off adders, and subtractor. In subtractor, we are going to discuss about the off subtractor and full subtractor. Full subtractor using two off subtractors and the binary adder. So first we will discuss what is combinational logic circuit. Okay, so here in combinational logic circuit is a circuit in which different types of logic gates are used to produce the output. Okay, so here the present outputs of the combinational logic circuit will depends on only present input values. Okay, so combinational circuit outputs depends on the only present input values. It will not depends on previous output values. Okay, so there is no storage elements in the combinational logic circuit. So the output of the combinational circuit is determined from the present combination of the input regardless of the previous input. Okay, so the input variables, logic gates, and output variables are the basic components of the combinational circuits. So here there are different types of logic circuits we have. For example, adder, subtractors, multiplexer, demultiplexer, encoder, decoder, all these comes under the combinational logic circuit, because the present output will depends on the only present input value. It will not depends on the previous input values. So by seeing this one, we can observe the characteristics of the combinational logic circuit as at any instant of time, the output of the combinational circuit depends on the only present input terminals. Okay, the present input values. So here the output will not depends on the previous input and previous output values. So here there will not be any storage elements in the combinational logic circuit. So the combinational circuit doesn't have any backup or previous memory. Okay, whereas in sequential circuits we have memory, but in combinational circuits we don't have any backup or previous memory. So the present state of the circuit is not affected by the previous state of the input. So here it has it may be it contains n number of inputs and m number of outputs. So the logic, whatever the logic circuit will be built by using logic gates in the combinational logic circuit. Okay, so in the basic combinational logic circuit is the adder. So in this session we are going to discuss about the adders and subtractors. Here we will discuss what is adder, what are the types of adder, and the construction of adders. Okay, so adders are digital circuits that carry out the addition of numbers. To add any two numbers or n numbers, we will use the adders. So basically adders will be used in ALUs, arithmetic and logic unit, and computers, processors. Okay, we will use these adders. And apart from addition, adders are also used in certain digital applications like table index calculations and address decoding, or increment and decrementing of the address. We will use these adders. For number system representation also we will use these adders, such as binary BCD or XS3 addition, or for the most common adders, operators are binary numbers. Okay, so to add any binary numbers, so 1-bit binary numbers, we will use the off adder and full adder. So the basic adders are off adder and full adder. So what is off adder? Okay, off adder is a type of combinational logic circuit where two numbers will be added. Each number will be represented as 1-bit binary number. Okay, so the outputs of the off adder will be sum and carry. So here A and B we are taking the inputs. each bit A and B represents one bit binary numbers. Either it may be 0 or 1. B also one bit binary number. Either it may be 0 or 1. So the outputs of the off adder are sum and carry. Okay. So if we observe the truth table of the off adder, so just we are going to add A plus B. A is one bit binary number, B is one bit binary number. If we have the two inputs means we will get the 4 combinations. Okay, 0, 0, 0, 1, 1, 0, 1, 1. So if A is 0 plus B is also 0, if we add 0 plus 0, we are going to get sum is 0. We are not getting any carry. So carry also we are going to write 0, 0. Okay. So for 0 plus 1, next to 1. Okay, 0 plus 1 is 1 is sum and we are not getting any carry. So carry will be 0. Sum is 1, carry is also 0. And 1 plus 0, sum is 1. We are not getting any carry. So sum is 1, carry is 0. But for 1 plus 1, in binary bit addition of 1 plus 1, we have to write here, we will get the sum is 0 and carry is 1. So this is sum, this is carry. So if we take the decimal equivalent of 1 plus 1 is 1 and 1. If we add these two, we are going to get 2 in decimal. So 2 will be represented as 1, 0 in binary. Okay. So this 0 is sum, carry is 1. Okay. So if you can remember like this also. Okay. So sum is 0, carry is 1. So 1 plus 1, this is, we have to remember 1 plus 1 is sum is 0, carry is 1. Okay. So this is the basic off adder truth table. So here if you want to write the equation for sum in terms of the inputs, here if we observe the truth table of this A, B and sum. Okay. So here in this, if you observe this truth table, so A, B, sum. So for if both inputs are 0, we are getting 0. Otherwise, we are getting 1. So this is the truth table equivalent to the XOR operation. So directly we can write sum is equal to A XOR B. Okay, the equation is equal to the A B bar plus A bar B. Okay, so if you observe the equation for the carry here, for the 0, 0, A, B are 0, 0, 0, 1, 1, 0, 1, 1. The carry is 0, 0, 0, 1. So this is the truth table. So if both are ones only, we are getting 1. If any one of the input is 0, we are getting 0. So this is the truth table for the AND gate. So that's why we can write the carry is equal to A into B. So the equation for sum and carry are sum is equal to A XOR B and carry is AB. So by using those equations, we can draw the logic diagram. So A XOR gate will be represented by, so we are giving input A and B, we are going to get A XOR B. Okay. So that is the sum. And for carry, we have the A into B. So A into B is given. So if A into B means AND gate, it acts as a multiplier. So here we are going to get A. Okay, this is the logic diagram of half adder. If we go for full adder is used to add only, half adder is used to only add 2 numbers. Each number represents 1 bit binary number. But if you want to add 3 bit numbers, 3 numbers, each number represents 1 bit binary number, then we will go for full adder. For example, 1 plus 1 plus 1. If we 1 plus 1, directly we can use the half adder. But if we want to add the 3 numbers, each number represents 1 bit binary number. For that, we will use the full adder. Okay. So the full adder is used to add 3 1 bit binary numbers. Here A, if you observe this block diagram, A, B, C are the inputs and sum and carry as the outputs. Okay. The truth table for the full adder is here. Okay, here the truth table is here. We have 3 inputs. So for 3 inputs, we will get the 8 combinations: 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1. So for that we have to get the sum and carry. So here 0 plus 0 plus 0. So if we are adding the all zeros, we will get the sum 0, carry also. We are not getting any carry, so carry also 0. Okay. For 0 plus 0 plus 1. For 0 plus 0, 0. 0 plus 1 is sum is 1. We are not getting any carry, carry is 0. Okay. And for third one, 0 plus 1 plus 0. That one you will get the 0 plus 1, 1, 1 plus 0, 1. So 1 we are not getting any carry. Okay, 0 plus 1 plus 1. Okay, so 0 plus 1 is 1. 1 plus 1, we are half adder 1 plus 1 is sum we will get the 0, carry we are going to get 1. Okay, so 1 plus 0 plus 0. So 1 plus 0, 1, 1 plus 0, 1. So 1 carry 0. So 1 plus 0 plus 1. 1 plus 0, 1. 1 plus 1, sum 0, carry 1. And 1 plus 1 plus 0, 1 plus 1 is, sum we are going to get is 0 and carry 1. 1 plus 1, 1 0 we are going to get. Again we have to add. So 1 0. This is sum, this is carry. So it is 0, it is 1. Okay. 1 plus 1 plus 1. This is very important. 1 plus 1 plus 1. First we are adding 2 ones. Sum 0, carry 1. 1 0. This is sum, this is carry. Again we are going to add 1. So 1 plus 1, 1 1. 0 plus 1 1 and carry 1. So this is 1 sum, this is carry. Okay. So 1 1 we are going to get. So this is the truth table of the full adder. Here A, B, C, N are the inputs and sum and carry are the outputs. So to get the equation for sum and carry, we should represent output in terms of input variable. Okay, for that we have to draw the K map. So it is a 3 inputs. We have 3 inputs. So we will use A 0 1, B C in 0 0 0 1 1 1 1 0. Okay, we have to note down the values where we are getting 1 for the sum, where we are getting 0 0 1 we are getting 1 and 0 1 0 we are getting 1, 1 0 0 we are getting 1 sum and 1 1 1 also 1. So 0 0 1. So 0 0 1 we are getting 1, 0 1 0 we are getting 1. Again next one 1 0 0. So 1 0 0 we are getting 1, 1 1. So sum we are getting for these variables. So no one will be paired with another one. Directly we can write sum is equal here for this one. This one is A. 0 represents B bar, C represents C here, C in bar. So B bar, C in bar plus this one A is 0. So A bar. Here B is 0. B bar. C is 1. So direct C. Here this one is A, B, C. And for this one A, B, C in bar. Okay. So we can write that sum is here this will be equal to A XR, B XR, C in. Okay. And carry, if we go for carry, okay, carry A, B, C in 0 0 0 1 1 1 1 0 0 1. Okay. So where we are going to get, we have to note down those values and make that mark that ones here. Okay. So for this one we have to pair these 2 ones. So we will get the carry is equal. This is A, this is C, and we can pair these two ones. For that we can write B, C. For this we make these two ones, that is B, A, B. Okay, so these two are the equations for sum and carry. So we can write this as A XOR B XOR C in. Okay, so sum is given to the 3 input XOR gate. We are going to get A XOR B XOR C in, and for carry AB, AC, BC. So these products will be given to the AND gate. So here you will get the AB. So A, B is given here. Okay, and A, this one is C in is given here, and C in B is given here. So AB, AC in, BC in. So these will be added by using the OR gate. So the plus symbol indicates the OR gate. Okay, so here AB plus ACN plus BCN. So this is the logic diagram of the full adder. So if you want to design full adder using two off adders, okay, here for that we will use two off adders and one OR gate to design full adder using off adders. Okay, so here first off adder is given name as A, second off adder given name as B. For that first off adder, the inputs totally full adder has inputs A, B, C. Okay, so first off adder inputs are A, B. Okay, so here we are going to get A XOR B. Outputs of the off adder is A XOR B and AB. Okay, and the output of the first off adder is given to the sum is given to the input to the next off adder. Another input is C. Okay, and the output of the carry output of the first off adder is given to the input to the OR gate, and second carry off adder carry is given to the input to the OR gate. Okay, so if we write the off adder circuit in terms of gates, off adder will be represented as XOR gate and AND gate. So here AB is given to the XOR gate. Here we are going to get A XOR B, and AB is given to this AND gate. Here we are going to get AB. Okay, so the second XOR gate inputs are A XOR B and C. So the output will be A XOR B XOR C. Okay, and the second gate AND gate inputs are A XOR B and C. So AND gate represents it acts as just multiplier. So A XOR B will be multiplied by the C, and the OR gate inputs are A B and another input is A XOR B C. So A B plus A XOR B C is the output carry output of the full adder. Okay, so this is the equation for sum and carry by using two off adders. This is the logic circuit using off adders for the full adder. So off subtractor. Subtractor is used to make the difference between the any two numbers. Okay, so here off subtractor is used to it is a basic building block to subtract the two binary numbers. It has two inputs and two outputs. So two inputs, the circuit is used to subtract two single bit binary numbers. Okay, the outputs, inputs are A and B. We are taking the outputs, we are taking as difference and borrow. So A minus B, after subtraction we will get the difference. If we are A minus B, B is the greater than to the A, we will get the borrow. So if we go for truth table, for A minus B, we have to perform. A is A and B both are 1-bit binary numbers here. So we will get the 4 combinations 0, 0, 0, 1, 1, 0, 1, 1. So for all the combinations, what are the difference and borrow we have to observe. 0 minus 0, we are not getting any difference and borrow. 0 minus 1. So here we are subtracting larger number from the smaller number, we will take the borrow here. So 0 minus 1 is 1 and borrow we have to take the 1. So 1 and 1 we are going to get. 1 minus 0, 1 and borrow is 0. 1 minus 1, if both numbers are same, we will get the difference is 0. We are not taking any borrow. So borrow is also 0. So for this, if we observe the truth table, for difference equation, if both inputs are same, we are getting 0. If both the inputs are different, we are getting 1. So it is simply like A XOR B. Okay. For borrow, here if you observe for A 0, B 1, we are getting 1, otherwise it is 0. So we can write that as A bar B. Okay. So here we know the equations of difference and borrow. By using these equations, we have to draw the logic circuit for the half subtractor. Here we know the difference is A XOR B. So both A and B given to the XOR gate, we are getting A XOR B. But the borrow is A bar B. Okay. So to get borrow A bar, so A bar A is given to the NOT gate, then we are going to get A bar. So that's why we are using NOT gate here. A is given to the input to the NOT gate, we are getting A bar, and B, A bar and B given to the inputs to the AND gate. So we are going to get A bar B. So full subtractor. Half subtractor is used to subtract the two numbers. Each number represents one bit binary number. But full subtractor is used to 3 number subtractions. Each number represents one bit binary number. Okay. So A, B, borrow in, B in are inputs and difference and borrow are the outputs. So A, B in are the inputs which are the only represents one bit binary number. So we have to perform the subtraction between the A, B, C in. We have to get the output as difference and borrow. If you observe the truth table of a full subtractor, here A, B, in borrow are the inputs, difference and borrow are the outputs. So 0 minus 0 minus 0, we will get 0, 0. 0 minus 0, 0. 0 minus 1 is 1 difference and borrow is also 1. 0 minus 1 is 1 is difference and 1 is borrow. From that we have to subtract 0. So same results we will get. So 1 is different, borrow is also 0. So 0 minus 1 is 1 is borrow, 1 is difference. Okay, again we have to subtract 1 here. So 0, 1. So difference is 0 and borrow is 1. 1 minus 0, 1. 1 minus 0, 1. So difference is 1. We are not taking any borrow here. And 1 minus 0, 1. 1 minus 1, 0. So difference 0, borrow 0. In 1, 1, 0, for 1 minus 1, here 1 minus 1, 0. 0 minus 0, 0. So difference is 0, bar is also 0. 1 minus 1 is 0. Again we have to subtract 0 minus 1. So 1 is difference and 1 is bar. Okay. So this is the truth table of the full subtractor. And here the difference and borrow are the inputs. By use draw the K map for the truth table. So A, B in bar are the inputs. So we have to mark the where we are getting ones. So for 0, 0, 1 we are getting 1. So 0, 0, 1 we are getting 1 and 0, 1, 0 also we are getting 1. Another one for 1, 0, 0 and another one for 1, 1, 1. So mark those ones. So there will be any, we are not getting any pair combination here. So we have to write the equation for this one. So here for this one, A, these are 0 represents B bar, B in bar. So A bar, B bar, B in. So this term we can write as A, B bar, B in bar. This here A is 0. So we will write A bar. Here B, B bar. 1 is B in. Okay, for this term, this is A, B, B in. All are ones. So this term we can write A bar, B, B in bar. So write that equation which is equal to the A XOR B XOR B. Okay. If we write the equation for the borrow, if we draw the K map, we have to mark the where we are getting ones and pair the ones here. So for this one, what we will get the literal here? This one A, B, B in, because 1 1 both we have 1 1, so B in. If we for this one we will get the A bar B, and if we pair these two ones we will get the A bar B. So add these letters, we will get A bar B in, A bar B, B in. Okay. So here by these two equations we have to draw the logic diagram of the full subtractor. So for difference we are going to get A XOR, what is the equation? A XOR B XOR B in. Okay, so these three inputs given to the XOR gate, we are going to get difference. Okay, if we observe the bar difference equation, A bar we are using here. So to get A bar, we have to use this NOT gate. The input is A here, output we are getting A bar. So here A bar, another one is B. Okay, another AND gate, inputs are B in, A bar. For this AND gate, inputs are, we are getting from here B and B in. So AND gate just act as a multiplier. So A bar B, A bar B in, and this is B in. So we are going to get A bar B plus A bar B in plus B in. So this is the equation of difference for the full subtractor. Full subtractor using two half subtractors, and by using half subtractor, here we are going to use two half subtractor and one OR gate to design the full subtractor using two half subtractors. So first subtractor name is A and another one is B. So A and B given to the inputs to the first subtractor. The difference and borrow, we are going to get outputs for the first subtractor, and the first subtractor difference is given to the input to the next subtractor, and borrow is given to the OR gate. And second gate, second half subtractor has input borrow in, and another input is difference of the first half subtractor, and we are going to get here A XOR B XOR C. And for borrow of the second subtractor and first subtractor given to the OR gate, here we are going to get the borrow output. So this is the first logic of our subtractor logic diagram. We know logic of subtractor contains XOR gate, NOT gate and AND gate. This is another of subtractor. Okay, both borrows of the both half subtractors will be given to the OR gate. Then we are going to get the borrow. So this is the logic diagram of the full subtractor. And binary adder. So we have half adder. So here we are adding A plus B. A is 1 bit binary number, B is 1 bit binary number. For full subtractor, A plus B plus C, all are 1 bit, represents 1 bit binary numbers. So but for binary adder, if you are to add two binary numbers of any length, we will use the binary adder. So this is also called as a ripple carry adder also. So binary adder is formed with the help of full adder circuits. The basic element for the binary adder is the full adder circuit. So here, if the full adders are connected in series, the output carry of the first adder will be treated as the input carry of the next full adder. So this n-bit parallel adder is used to sum two single bit binary numbers with carry input. Okay, so here if we take the adder, so we are taking A contains 4-digit number A3, A2, A1, A0 suppose. B For example, it is B3, B2, B1, B0. So we are adding these two numbers. We will get the sum S3, S2, S1, S0 and carry C out. Okay. So this is the function of the binary adder. So this is the block diagram of the binary adder, where the basic element for the binary adder is full adder. So the full adder, we have inputs for full adder. See, for example, I am going to add 1 1 0 1 1 1 1 1. Okay. So here, if we add these two numbers, A is a 4-bit number, B is a 4-bit number. That is nothing but A3, A2, A1, A0. B has 4-bit number, B3, B2, B1, B0. Okay. So for first to add A0 and B0, but we have 2 digits. But full adder contains 3 inputs, A, B, C. So for that we are adding another extra bit C in. We have to make that as 0. Okay. So first of full adder has inputs A0, B0 and C. Here we are going to get sum is S0 and carry will be forward to the next stage. Okay. So that is C0. Okay. So the C0 and A1, B1 are the inputs. So A1, B1 and C0 are the inputs to the next full adder, where we are going to get the sum S1 and carry will be forward to the next stage, C1. Okay. C1, A2, B2. C1, A2, B2 will be the inputs to the next full adder. We are going to get the S2. Sum is S2 and the carry will be forward to the next full adder, that is C2. So C2, A3, C2, A3, B3 are the inputs to the next full adder. We are going to get the output S3 and final carry C out. So this is the basic block diagram of the 4-bit binary number. So if we take the example 1101 1111, so first we are giving a C in is 0 and A not B and not are 1 1. So 1 plus 1 is 0, sum and carry is 1. So carry 1 will be forward to the next stage and sum will be here 0. Okay. The second full adder inputs are, we have 0, 1 and inputs is another one is C0 is 1. So 0, 1 plus 0, 1, 1 plus 1, sum is 0, carry forward to the next stage. So sum is 0, carry is forward to the next stage. So A2 1, B2 1, C in 1. Okay. So the second full adder 2 has the inputs 1 plus 1 plus 1 plus 1. So if the 1 plus 1 plus 1 is, sum is 1, carry is 1. So here we are going to get sum is 1, carry will be forward to the next stage. So these 3 will be added again. Okay, 1 plus 1 plus 1. The final sum is 1, C out will be 1. So the total final answer will be C out. This is C out and 1 1 0 0. So 1 1 0 0 we are going to get the output by using binary adder. So this is the block diagram of 4-bit binary adder. So the books referred are Modern Digital Electronics by RPJ and John A. Packerley by using Digital Design Principles and Practices, and the diagrams are referred from the javapoint.com. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.